Welcome to Saravji's Hut. Today's topic is an educational talk about feature selection and feature engineering and why it matters. In this part, I'll cover feature selection. Feature selection. Why do we need it? The intuition behind feature selection is to reduce the features in the dataset to the features that support the signal and only use these to feed it to a machine learning algorithm. And of course, suppress that don't add to the signal because they are just adding noise. Feature selection itself is fundamentally different from feature elimination or dimensionality reduction. Feature elimination starts with all the features and eliminates the feature that adds the least value. And it's doing this by examining and comparing it to the remainder of the features. Dimensionality reduction is a mathematical process to transform the data into a data set that has fewer dimensions. Now, this transformation, which means we can reconstruct the original data set out of the transformed data. So we are not eliminating any part of the data in this way. Feature selection selects the features that actually add value. If you're looking at it in a graphical way, we have all our features, and a subset of our features is the features that actually add to the signal. The size of the relationship, how many of the features add to the signal to all the features, can differ, and that depends on the dataset. And then, of course, the next question is feature selection actually necessary? Wouldn't the ML algorithm just go and disregard or put less regard on unimportant features? No, not directly. So the intuition behind any ML algorithm is actually to optimize to the data as presented. And this specifically includes all the noise presented as well. So what actually happened is the low-hanging fruit, the easy fitting, is to the signal. But once the signal is exhausted, a machine learning algorithm now optimizes, instead of only on the small nuances in the signal, it also optimizes for the noise that is coming in from the unimportant features. And the ML algorithm now actually fits to the particular noise in this training set. Especially vulnerable are boosted algorithms because they are actually boosting the smaller or more unimportant areas of the data as they go along. Now, can tuning, cross-validation, or train test validate split compensate for this? Of course, to a certain extent. But first of all, it's computationally expensive and also time-consuming and quite a bit of a user effort to actually achieve small gains. So how can we do feature selection, or how can we get to the result of feature selection? So one method is to simply add one random feature out of all not yet included features at a time, and then evaluate which feature creates the biggest lift, the biggest improvement. And we repeat this until we don't see any more improvement. This approach is called forward selection. Another method would be to take all the features and subtract one at a time and evaluate, eliminating which feature creates the least reduction in the result. So If we are not affecting our result, then this means this feature is not contributing anything or very minor only. This way, we are reducing the total number of features one at a time. And we repeat this until removing any more feature is actually starting to have an effect on the results. This way is called backward elimination. Both these approaches have actually the negative effect that they are based on the particular characteristics of the data. Also, actually, the sequence in which we are adding or subtracting features can have significant impact on which further features are being eliminated or subtracted or added. So we are making ourselves extremely dependent on a random effect here of which feature we are actually starting with or which feature we are choosing to take next. So this means running this same process multiple times and choosing of more than one feature is a candidate to actually add or subtract. Choosing different ones ends up with vastly different results, or can end up with vastly different results of the remaining features of the final feature set. And this means that neither of these methods is actually solid enough that we can blindly rely on it. Now, there is another method that actually evaluates each feature against itself. How this works is a feature is being copied into the same data set as a shadow feature. What this means is the complete feature column is being copied, so we have all exactly the same values as we had. But then the sequence of the values in this shadow feature is being randomized, so that values are randomly assigned to the rows in the data. All the values are exactly the same, so the statistical characteristics of the two features are exactly the same. Just the relationship between the individual values and the row is getting completely eliminated. And then we're comparing, after fitting it to a machine learning algorithm, we are comparing the importance between the original feature and the shadow feature. And we're doing multiple runs, multiple a little bit slightly different characteristics, just to actually spread the probabilities here that we are not finding some form of a random lucky guess or unlucky guess. So we are running it multiple times with slight variations, and then we compare the importances between the original feature and the shadow feature. Now, if the shadow feature is the same importance as the original feature, or even more important than the original feature, this means that the original feature does not add any value. And we're repeating this for each individual feature. The big advantage here is we are taking the sequence and the dependency out of the picture here, so that we are actually not creating a necessary sequence based on the order how we are adding or subtracting features, because we are not comparing between with the feature or without the feature. We are comparing the importance between two times basically the same feature, the original feature and the shadow feature. It's the same data, and everything else stays the same. And with that, we are going to jump to the demo notebook for feature selection. See you in the next part, and thank you for watching.